Morning, Year 6. For science today, we're going to continue talking about mass and forces, and we're going to start shifting our focus more to the forces side of the sciences. Now, in our previous lesson, we spoke about how gravity and mass interact with each other, and how the mass of something is measured according to how much gravity pulls against it, and that's what we measure as a weight, either in kgs or in grams or in tons, depending on the size of that object. Now, what is it about gravity and friction that will cause the same piece of paper, this one's just got some writing on it, but it will cause the same piece of paper to fall at different rates? They both have the same mass, we agree. They're the same thickness, the same dimensions, but if I scrumple one up, what is it about friction and that force that causes the identical masses? Now you can see that they're different dimensions, but we have not changed the mass. The same amount of paper is still here as here. So if I drop these two together, because they're the same mass, we would expect gravity to pull on them the same amount. However, the force that we're going to be speaking about today that was introduced a few days ago is friction. And even falling through the air, you can see that this paper, it's flopping downwards right now, but as it falls through the air, it flops upwards. That is because it's coming up against the air particles which are pushing against it and causing friction and resistance. Now, if I had to drop these two papers together at the same rate, you would expect them to fall at the same rate because they're the same mass, but it's quite clear that there's a force acting on one of them more than the other now. And that force is friction. Friction between the mass of the paper and the air around it. Now, because I've scrumpled up this paper, there is less profile or less surface area of this paper falling through the air. So if you imagine these papers now falling towards the camera, as they fall towards you, they can't fall at the same rate, because this paper is presenting a larger surface area. So there's more air stopping this one from falling and less air stopping this one from falling, because it's got such a smaller surface area as it falls towards the ground. And that is the reason why they now fall at a different rate, even though they both have the same mass. Now, friction is something that scientists spend a lot of time and a lot of money trying to either improve or make less. So what I mean by that is there are certain instances in science and in physics where we need friction, and without friction we wouldn't be able to live. And there are other instances where we actually try and reduce friction as much as possible, or our lives would become very difficult again. Now think about it. I'm standing on the floor right now and I'm walking around in the classroom. There is a certain amount of force, friction, that is existing between myself and my shoes and the floor. There's also friction between myself and the air around me. Now, because I've got some energy and I'm able to push myself through the air, I don't really feel that friction, because I'm not really going fast enough. My mass easily overcomes the friction of the air. My takis are very sticky, so I've got a lot of grip, and that helps me change direction very quickly. However, if I had to take my shoes off and I no longer have the benefit of the sticky rubber sole underneath, what is going to happen with my socks? I'm now able to slide, because my slippery socks easily overcome the friction that is between them and the floor. However, the sticky rubber is designed in such a way that it really produces a lot of friction between the shoes and the floor, which makes me a lot more stable. So you can clearly see that there are certain instances in life where You would want a lot of friction, for example, when you're walking or playing sports, and when you'd want very little friction. For example, the wheels of your bicycle, the hubs. If those bearings were sticky and they didn't turn freely, it would take a lot of effort to turn those wheels. So you don't want a lot of friction at the wheels by the hubs. However, if the tires didn't have friction, you wouldn't be able to go around corners, you wouldn't even be able to accelerate. Think about braking when you need to use the brakes on your bike. If there wasn't friction there, you wouldn't stop. But at the same time, you don't want friction by the wheels, by the hubs, where they need to spin. You don't want a lot of friction by the chain, where it needs to be transferring your power to the wheel. So in the next few lessons, what we're going to be talking about is this force of friction and how we are able to measure it, and how it is that gravity uses the mass of an object to increase the amount of friction on a surface. And then we're going to talk about the different ways in which we can decrease certain amounts of friction in order to benefit us, and how we can increase friction in order to benefit us also. So as we go through this lesson, I'd like you to bear that in mind, and just keep in mind that this force of friction is determined by the amount of mass an object has. And some of the experiments that we're going to do will demonstrate how mass can increase friction. Because remember, the more mass an object has, the more gravity can pull against it. And the more gravity can pull against it onto the surface of something, the greater friction you'll experience. Okay, thank you for listening. Okay, so now what we're going to do is a few experiments just to demonstrate how gravity affects mass, and how the size of an object doesn't really mean that it has got an increased amount of mass. So to start off with, I've got a hockey ball. I've got the soccer ball that you guys are forever fighting over at break time. And I've got the globe that everybody keeps treating like a soccer ball. And I'm just going to stick them on the scale first of all, so that you can see the difference in their mass. So I don't know if I bring this a bit closer, if it'll be too close. Okay, that works. So this first of all is the hockey ball. I'm going to stick it in there. Let me just zero this scale first. Okay, so hockey ball is going into the scale. I think each one of these is 20 grams, 20, 40, 60, 80, 100 grams. That's roughly 100 grams for the hockey ball. Soccer ball. It's 4, 8, 12, 16, 20, 24, 280 grams for the soccer ball. And our globe, 40 grams. Okay, so it's very, very light. Now what I want to do is, now that you have an understanding of what the mass of these items are, is I'm going to stand on Philip's desk and I'm going to drop these one by one. Now I'm going to drop them onto this catch net that we use for cricket. And basically I'm going to allow gravity to act on their mass. That means they will be able to store up a certain amount of energy. If an item is small and smooth, and it has got a good amount of mass for its size, there is a lot of mass for gravity to act on, and there's a small surface area for friction to act on also, which means, what is your prediction? This ball should be the one that drops with the most force, and we will see this in how high it bounces off the catch net. So I'm going to start off with the globe first of all. I'm going to drop it from my height, so they're all going to be the same. Right into the middle of the net. I'm just going to let it go and we'll see how high it bounces. Okay, I'll take another one, straight into the middle, watch it fall and see how it bounces. Okay, and now I'm going to go with the soccer ball, watch it fall and see how high it bounces. Okay, and we're going to do it again. And now I'm going to do the hockey ball and see how high this bounces. And again. So that's interesting. I would say that both the hockey ball and the soccer ball were very close in height. Now if you think about it, the soccer ball is 4 times the mass of the hockey ball. The hockey ball we said was about 100 grams, the soccer ball was close to 400 grams. They have the same mass, but for some reason, they don't have the same mass. The soccer ball has got a mass 4 times greater than the hockey ball. It looks even 4 times bigger. But for some reason, it looks to me like they're bouncing the same height, very close to the same height. Okay, it won't work if they do it together. Let's take this one and this one. Very, very similar bounce height. Now, the only reason that could be is because, despite having different masses, the hockey ball is able to fall at a greater rate because there's less friction acting against it. It's got a smaller surface area. So even though it's lighter, its mass is being pulled more efficiently by gravity, which means it's able to store energy better and it rebounds that energy better. The large ball, even though it's heavier, gravity can pull it down more, but because it's got a surface area that is rough and larger than the hockey ball, it seems to be falling with more friction acting against it. So even though it's 4 times bigger and 4 times heavier, it doesn't mean that it's going to be more efficient than the smaller, smoother hockey ball. Now I want to do a controlled experiment where I've got 2 containers that are exactly the same. They're those normal yogurt containers. This one is empty. This is the one that the protractors and stuff live in, so I've taken all of them out. I'll just zero this again. Okay. That wasn't on 0. So that looks like it's just over 20 grams. Maybe 23, 24 grams. That's the empty container, and this one that's full of counters, and I really, really hope that this stays closed and it doesn't end up all over the classroom floor, otherwise Taylor will have something nice to clean. Right, that's 540 grams. Let me just get some sellotape quickly to make sure that this doesn't close. No, it doesn't open, because I really don't feel like picking up 1,000 counters today. So, the one that's blue, that says counters on it, this is the one that's 540 grams. And the one that is white, that says protractors and compasses on it, this one is empty. This weighs just over 20 grams, just the container by itself. So now what we're trying to do here is we're trying to eliminate shape and size. Remember before we did the experiment with the 3 balls, there were different shapes, different sizes, different textures, different masses. They all bounce differently. So now I want to demonstrate just the mass alone. We've got identical containers. Theoretically, they should do exactly the same thing as they fall through the sky. But because one is heavier than the other, it means that this one is going to allow gravity to act on it more. It's going to have more mass, which means it's able to store more energy as it falls through the sky. Gravity can accelerate it more. It has got more mass, which means it's going to overcome friction better than this one. So let's have a look. We'll do them one at a time. This is the empty one. Let me just move that scale out of the way. I'm trying not to break my neck. Right, let's try that again. So the empty one. And the full one, please stay closed. A big difference, a very big difference. The empty one again. And the one that's full of counters. Right, so that clearly shows that once we get the shape and size out of the way, mass definitely does affect the amount of force that gravity applies on something, but it also affects friction. And the next experiments that we're going to do are going to show how we can measure friction. Now, in the previous clip, I'm joining these all together. In the previous clip, I explained basically how gravity can affect mass, And the greater mass an object has, the more friction it has, or it's a force that Isaac Newton spoke about, and it's called inertia. But I want to speak more about those in a different lesson. For today, the demonstrations between mass and friction falling through the air, I think, will suffice. In the next lessons, I want to now talk about surface friction and how the weight of something affects how easily it can be pulled or how difficult it becomes to pull. And then we'll be looking at those spring scales that are called Newton meters, and they were named after the force Newton, which was named after the scientist Isaac Newton. And the rest of the lessons coming up will be very physics based, and they'll be talking about how the mass of an object can affect its friction value and can affect how gravity acts on it. And words like inertia, we'll be speaking about inertia, we'll be speaking about acceleration, deceleration, the friction and the masses that we've been speaking about all this time. So it's going to be a lot of experiments, it's going to be a lot of demonstrations, which does mean that you'll have quite a bit to watch and quite a bit to make notes of. And then right at the end of the lesson, I'd much rather have us doing the academics where we actually make note of an experiment. But for now, your task with this lesson that I've just put together is to make notes of what you've seen, make notes of the experiments that I've set up here, and just remember that it is very important for you to have your estimations of each experiment. Just before you see me doing an experiment, what did you think? How did you feel? What did you think about how it would have turned out? Was the outcome what you expected, or was it something different? That is what will help me to understand whether or not you have fully grasped what we're speaking about in terms of mass and force of friction. The next lessons will help explain it a bit more. So I hope you enjoyed this. Try a couple of these experiments at home if you want. Try different size balls if you've got ones that have got air in them and ones that don't have air in them. And let's talk about why they bounce differently. The catch net here was just to control the bounce. Because it's going to produce the same amount of elasticity, it doesn't matter. That doesn't come into account when we're dropping objects on it. It will always rebound the same depending on how much force or how little force an object is applied to it. Okay, so make your notes. Let me know what you think of this lesson, and we shall catch up in the next one. Thank you very much.